Start off by pausing and copying those notes. Today's topic's hybridization. You need a periodic table out if you don't already have one. We're going to start today off by revisiting Lewis structures, which are real easy, but it's a good starting point to show you the purpose on why electron configurations actually do this thing you didn't know they did. So what I want to start off by doing is let's take a look at nitrogen. So look at nitrogen on the periodic table. If I was drawing his Lewis dot structure, how many dots does he get? 5. Because remember, Lewis dot structures show valence electrons. Nitrogen's in group 15, therefore he's got 5 valence electrons, so we would give him 5 dots. And remember, you were taught to put 1 on each side before doubling up. So that's what he would look like. Now, that's still true. But I want to analyze him in a slightly different way. What if I were to tell you that looking at this Lewis structure, it showed us places that he wants to bond? Really, the way that I know regions that an element wants to bond is where he's got 1 electron hanging out and room for another electron to come in. Because if that were true, then they could share electrons, him and somebody else could share electrons at that location. So listen again. Everywhere there's 1 electron hanging out by himself is actually giving an opportunity for another electron to slide in that spot and share. If that's true, how many bonds does nitrogen want to make? 3. He wants to make 3 bonds. 1 there, 1 there, and 1 there. What vocabulary do we give the region that I didn't point an arrow at? And he's got 1 lone pair. Would be the reason that there's not another bond. All right? So, that's nothing new. We're analyzing something old in a new way. But that should be pretty easy. All right? I want to do another one. Let's take a look at fluorine to make sure that you understand what's happening here. How many how many dots does fluorine get? 7 from group 17. Perfect. All right, so you put 1 on each side before doubling up, and he'd end up looking something like that. Following the same logic, how many bonds does fluorine want to make? 1. Yeah, 1. He would like to do 1 bond. Right there is where something else would come and bond to him. And we would say he's got 3 lone pairs. All right, so this should be pretty simple. But one of our stars for today is carbon. So real quick, do the same thing for carbon by yourself. Analyze carbon in the exact same way. All right, so help me out with carbon. I'm only talking to one person. How many dots did you give him? 4 is perfect. All right. How many bonds did you say you could make? 4 is a good number. How many lone pairs did you say he had? None. 0 lone pairs would be the other value to write there. We all good? Okay. Now, this represents information that you understand, that you know, because in the last unit for Vesper, we used this idea, and we could bond things to carbon while drawing our molecular shapes. The problem is there's an inconsistency here with something you've already learned. I want to show you now the orbital notation for carbon from way back when and show you that they don't match up because you weren't given the whole truth back then. So, if you have your electron configuration brain on, you know that we always start with 1s. We know that s can hold 1 orbital, and every orbital can hold 2 oppositely spinning electrons. That's review. Again, you're welcome to watch the electron configuration video to catch yourself up to speed. But what comes after 1s? 2s, all right, which is identical to 1s except for the energy level. And what comes after 2s? 2p. All right? P had 3 orbitals, but we don't want to fill them up because carbon only has 6 total electrons. So how many more arrows does that 2p need?
2.
Just 2. All right, so there's some review. All right, we had 1s2, 2s2, 2p2 is what it came out to. And here's where I want you to see the problem. Our idea is that every time there's one electron hanging out by himself, that's a spot where a bond can happen. Because if there's one electron by itself, it's like an atom saying, hey, I'm open for business to bond, but I need someone else to come and put an electron here so that we can share and grip onto each other. If that's true, how many bonds does the electron configuration say carbon can make?
2.
Just 2. One there and one there. There's no room for another atom there, and carbon has no representation of anything there. The only places that something could slide in and bond would be in these 2 locations where there's single electrons, and that's the problem. The configuration says carbon can make 2 bonds, but we know that's not true, which is why this isn't true. All right, the orbital notation that I showed you how to draw has been false, and now that we know how to draw molecules, I want to correct it. And it's called hybridization. What does the word hybrid mean? If you have a hybrid of something, it's 2 things that are... A hybrid does what with 2 things? It mixes them. All right, 2 different things are called 2 different things. All right, a hybrid is a mixture of 2 different things. Like a hybrid car is an electric car with a gas car. All right, we can correct this. We can make this work by mixing orbitals together. And that's actually what they do, is they will hybridize. Now, we're talking about bonding though. And there's one type of electron here that isn't a part of bonding. Which type of carbon's electrons do we not care about? See those inner shell electrons? They're not a part of bonding. Remember, valence electrons are all we care about. So yeah, the 1s is there, but it's not going to dictate any of the stuff that we're doing because the valence electrons are in charge of actually building molecules.
You can get rid of the 2s as well.
All high energy electrons. Remember, it's the number, not the shape, that dictate the energy. So here's what we're going to do. I'm going to show you how to hybridize carbon. It's going to be exciting. I want to mix them together. That's what a hybrid is. We want to mix them. All right. So to mix them together is kind of like to add them together. We're just going to push them together. If I push these 2 ideas together, how many orbitals would there be? How many lines would there be? 4. All right. I pushed them together. Watch. If you push them together, they'd be 4 lines. 1 and 3. All right. Cool. Hey. Of these 4 lines, see the 4 lines? Do you see the 4 lines?
Yes.
Of the 4 lines, how many of them came from S?
1.
Just 1, right? He came right down there. So I'm going to put just an S. That would represent a 1, right? We know that if we don't show numbers in chemistry, it's a 1. So there's the S. So if 1 of them came from S, how many came from P?
3.
Yeah, look. 1, 2, 3 came from P. 3 came from P. I would say that carbon has a sp3 hybridization. And again, nothing crazy here. I took the valence electrons, I pushed them together. It made 4 lines. 1 of the lines came from S. 3 of the lines came from P. But now, if you follow, not off-ball, if you follow Hund's rule, how will the electrons fill this?
1 at a time.
How many bonds can carbon make now?
4.
Ah.
Wow.
That's what I was just thinking first.
This is hybridization because it makes the structures right.
Is it for everyone? Like nitrogen?
Right. I'll show you nitrogen next. All right. So this is the hybridization of carbon. The answer is actually sp3. That's the question I get a lot. Well, so the arrows are the answer? No. The hybridization of carbon is sp3. That's the answer. But this is just what it looks like, because questions could ask you to go a step further than just the sp. Now, I want you to take a look at how this actually translates into a compound. All right, so here's a common compound. This is carbon tetrafluoride. All right, and now all of this lines up, because this is telling you that carbon we know can make 4 bonds. Here's the room for all 4 of those fluorines to snap in his sp3 hybridization. And really, what's happening here is we know that fluorine has 7 valence electrons. He'd have another one right here, but how many electrons are in that bond? There's 2. All right, so it's really this that's being shared. But one of them would come from fluorine, because we know that fluorine started off with just 7 dots. And the other one would come from carbon, all right, which it would be that guy right there. So really, this fluorine dot is sliding into that spot to bond, and that dot was already there from carbon. That's kind of a messy picture. I won't ask you to analyze it that way. I just want your brain to see why this happens, why it's necessary, because it wasn't true with the original configuration. I want you to write down an important sentence, though. There's only 2 types of things that hybridize. I want you to write down that sigmas, which is a new word, sigmas and lone pairs are all that hybridize. If you don't know how to spell sigma, it was on the notes you took at the very beginning of class. Sigma and lone pairs are all that can hybridize. Cody, question?
I was saying, are you saying in or and?
And. Sigmas can hybridize. Lone pairs can hybridize. And I'll show you what I mean. And in that sentence you just wrote, where you wrote sigma, right somewhere near it in parentheses, put single bond. Because they're kind of the same thing. Right close to where you wrote the word sigma, in parentheses, just put single bond. And I'll elaborate on that in a moment. All right. Now, I want to show you an example that uses a lone pair so you don't think I'm crazy. Draw this molecule. I'm focusing here. Now, if I had more time in class, I would have said, hey, draw NH3 real quick, and given you a minute, because you know how to draw this. All right, this is ammonia. He's sitting here with a trigonal, pyramidal shape, all this stuff that you already know that you'll still have to use on your test next week. What I want to do is hybridize it. All right, so here's my question. I want to know, what is the hybridization of that nitrogen? I'm pinpointing a part of the compound. I want to know the hybridization of that nitrogen. Well, in order to do that, I need to look at his configuration. Now, nitrogen has just 1 more electron than carbon, so it's pretty much the same thing. All right? His valence electrons will go into 2s and 2p. All right? But I said he's got 1 more valence electron, right? So, what will it do here? Y'all are so quiet.
Yeah, it'll double up on the first orbital.
All right, so carbon compared to nitrogen is exactly the same, except nitrogen has 1 more electron. But I want to know his hybridization. All right? Let me get through it, then I'll call you. All right? So let's mix them together. Remember the hybrid. All it is, mix them. If I mix them, how many lines will I have now? How many orbitals? 4. Any questions there? Anybody not see how I get 4?
Is it SP4?
All right. Of those lines, how many came from S? 1. So just S, no number. How many? If 1 comes from S, then how many came from P? 3. Hey, look, it's the exact same, right? It's sp3 again. This nitrogen has the same hybridization as carbon in the previous example. But watch, there's a cool representation here on the way nitrogen really exists. Now, Hund says that we go up, 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 up. But what does nitrogen have?
One.
He's got one more. He's got 5 electrons. So there's one more. And now you'll see that by going into a hybridization, it's perfectly represented because there's room for 3 bonds. And then what's that guy? A lone pair. Cool, right?
Whoa.
In order for me to take this further like I need to, we need to talk about the 2 types of bonds. And you wrote them down at the beginning of class, sigma and pi. So I need you to know a little bit about the way that these things bond together when they meet each other. So here's a very terrible picture from me of the way it looks. All right? If we have 2 compounds that are coming near each other, one of the associations is going to be a circular association. All right? And this is sigma. All right? This simple circular bond right here is a sigma bond. A pi bond is going to do this. And it's actually an attraction or a bond here. All right? These blue guys are the pi bonds. Sigmas are simple circles. Pi's have this dumbbell shape.
What's a dumbbell?
Figure 8. A couple things. Yes, ma'am.
Is the pi always going to be over the sigma?
Real quick, a molecular fact about this before we go into more detail. Because of the way this is shaped, sigma bonds can actually rotate. You'll want to mark that. You can rotate sigma bonds because of the way they're oriented with each other. Sigma bonds can rotate. Pi bonds cannot. If you look at the way the pi bonds are, if you were to try to rotate the pi's, it would break the sigmas. So it's important to know that the simpler bond can rotate, the sigma can rotate, the pi cannot. All right, so here's the deal, sigma versus pi. It's real simple. Anytime 2 atoms are going to bond together, sigma. Got to have a sigma. If 2 atoms are going to bond together in any one direction, it's a sigma bond. All right, that initial S. You only get pi bonds when double and triple bonds show up. All right, but the first bond before the double and triple would still be a sigma. You always have a sigma, and then doubles and triples can introduce pi's. And let me show you what I mean. Hang on to that, Cody, just in case I address it here. Now, I've got a molecule here that's made up. You can't hear me when I'm not. That's made up of a bunch of different stuff. All right, and some of them are sigma and some of them are pi's. Before I get into how to hybridize them, I want you to be able to just recognize them, and it's super simple. All right. Remember, anytime 2 things bond, it's sigma. Now you need to know a couple symbols. All right, these are Greek letters. That's sigma, and you probably already know pi. All right, sigma pi.
Yeah, how do you draw the sigma?
It's an O with a line going out. It's just an O with a hat saying good day, mate. Type thing.
Good day, me. Oh my god.
Hope you're not Australian if you're watching this. I'm sorry. Got a lot of subscribers in Australia. Okay. I'm going to count sigmas. Here we go.
Wait, do we have to draw that?
Sigma. You can draw the next one. Just watch. Sigma. Sigma. All single bonds are sigma. I'm going to skip him for now. Sigma. Sigma. All initial bonds are sigma. 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 I'm going to skip the triple for a second. Sigma. So right away, you can assume that all single bonds are sigma. Now let's look here. let's look at the double bond. Are there any sigmas there? Yes, because anytime two atoms bond, has to be a sigma. You can't have a pi without a sigma. So one of them, I don't care which one of them is sigma. What's the other one? Pi. Because all second and third bonds between an atom are pi bonds. The figure eights. Alright? Therefore, how many sigmas are in this one? One. Because you always gotta have one. Sigma. How many pi's are there? Two. And we all wish we had two pi's, right? Lunch. Okay. So then let's answer the original question. I wanted to know how many there are total. How many sigmas? 1, 2, 3, 4, 5, 6, 7, 8, 9 sigmas. How many pi's? Tree. Questions? Yes, ma'am. You try one. This one you should draw so you've got complete notes. Look here, don't draw yet! I've done something chemistry to you. You see that? It says CH2. You need to understand that that is a condensed molecule. Right there, it's CH2, which looks like this. Why is that important? Because that is a sigma bond, and that's a sigma bond, but they are not drawn. But you better count them. Now you're thinking, oh, so he's trying to make this hard. No, this is chemistry. This is how chemists write, so I need you to be able to count it. Hey, look, OH. Be careful. How many sigmas and pi's? Pause and count. Somebody broke Aspen last class. You know who you are. Okay. How many sigmas did you count? What? All right, quiet. He says he's got the pi's, but how many pi's? There are 3 pi's. All right, you got pumpkin, apple, cherry cobbler. Pie jokes are always funny. No?
I'm not laughing, so.
The 3 pi's are 1 there and 2 there. Are we okay with that?
Yes.
All right. Count the sigmas yet?
I got 1, 2, 3, 4, 5, 6, 7 right now.
7's his number. Do you agree or disagree? I disagree.
Oh no, what?
Let's find all 8 of them. Here we go. Here, there's 2 I can't see. The carbon bonds to the hydrogen for 1 sigma, bonds to another hydrogen, I'm at 2. All right? Then there's 1 there in the double bond, that's 3. There's 1 there towards hydroxide, 4. There's 1 there in hydroxide, because that O will bond to the H, 5, 6, 7, 8. So here's a more challenging hybridization. Here's what I've been trying to get you to today. Write this. It's a double bond in the middle, my bad.
Wow.
All right, we're working together. Here we go. Here's my question. I want to know, what is the hybridization of that carbon? All right? We're still working together. That one there. All right, they're actually identical, so we're good. But let's look at the hybridization. Here we go. Now look, I still have carbon's information up here for simplicity. There's his valence electrons. All right? But look at this carbon. Here's what I need to know. Here's it real quick. True or false? Pi bonds hybridize. How do you know that's false? Because what did you write earlier? Only sigmas and lone pairs hybridize. Which means anytime you find a pi bond, he's not going to hybridize. And we're going to show that here. Hey, look at the carbon that we're looking at. How many sigma bonds are there? There's 3 on it. He's got 1, 2, 3. He's got 3 sigmas. I'm just going to make a note so I know that. Do you see the 3 sigmas?
Yes.
Right away, I know then that I've got 3 orbitals then. They will match. The number of sigmas is the number of orbitals that need to be hybridized. That makes sense. You only hybridize sigmas. We've got 3 sigmas. We better need 3 orbitals then. They'll match up. And now let's look at carbon. We're talking about carbon. If I've got 3, how many came from S? 1. So just S, don't give them a number. So if 1 came from S, how many came from P?
2.
The answer is sp2. This carbon is sp2. Now I'm going to finish drawing the picture because sometimes you'll have to do that. But I want you to understand that we've just answered the question. What's the hybridization of that carbon? Sir, the hybridization is sp2. Now what does it look like? Well, off ball. I keep doing that. Hun. Up, up, up. And look, there's the 3 connections that he made. All right, there's the 3 bonds. That's the whole point, is hydrogen, hydrogen, and carbon locked in there to bond to them. So we're done with that part. But now with the pi, there's something else. We didn't account for all the orbitals. There's 4 orbitals, but we only drew 3. So the other one is still there. He's still there. He's just not hybridized. This is the pi bond. It's just 2p. All right, it was just 2p is that other orbital. All right, but there's actually still 1 electron left. So keep in mind that while you're coming up with the hybridization, you're drawing this. You owe all of that. You owe 4 orbitals and 4 electrons when you're doing carbon. 4 orbitals and 4 electrons. It's just he's sp2 because of his different number of sigmas. Let's do another one. Any questions before I move to another one?
What just happened? I didn't say the
Let's take a look at this. We're still working together. I know you still need me. It's really easier than your brain is trying to make it. All right. Now, again, I'm going to pinpoint one of the atoms. All right. So let's pick this one. I want to know what is the hybridization of that carbon. First question you want to figure out: how many sigmas?
2.
All right. How many sigmas are touching him? He's got 2 sigmas. There's 1 in the double bond and 1 in the double bond. All right? So then right away, if there's 2 sigmas, that means I need 2 lines. Right there. Boom. They're connected. However many sigmas is the number of orbitals that will hybridize. All right? And now we figure out where the heck did they come from? Well, let's look at carbon. We're doing carbon again because that's on purpose so that we can make it before the period ends. All right. How many of those 2 lines could have come from S?
1.
Well, he only has 1 to give. He only has 1 to give. So S. All right. So 1 of them came from S. Therefore, how many came from P?
1.
So this one, the answer is sp. This carbon has an sp hybridization. So then what does that look like? Well, Hun says up, up. And we'll definitely stop there, which shows the room for 2 things to come in and bond to that carbon. But let's keep in mind that this is everything we need to account for. So now we just need to figure out what we didn't hybridize. How many orbitals did we not hybridize? 2. All right, and they're both going to be in 2p. All right, those are the pi's because you can see that there's 2 pi's. All right, and then follow Hun's rule. The answer to my question, sp. The entire configuration after hybridization, well, the rest of what I drew. Before I answer your question, how many sigmas are in the entire molecule? How many sigmas are in the entire molecule?
6.
6, right? 'Cause, hey, look here. This is C bonded to 2 H's. So 1, 2,
6.
3, 4, 5. That would be 6 sigmas.